Greetings and welcome to my talk about cloning Postgres databases on Kubernetes. My name is Oleksii Kliukin, and I am a senior cloud engineer at Timescale. And in this talk, I'm going to tell how we designed database forks in Timescale Cloud, a managed database as a service. I work at Timescale, and Timescale creates Timescale DB. It is a Postgres extension, free and open, to handle large amount of time series data and provide convenient functions to run analytics of it. Timescale implements what we call a hypertable. It's what looks like a Postgres table, but it is partitioned in the background. We call those partitions chunks. Typically, times column is a partitioning key, and chunks are created automatically in the background, and a query for time series data will only go to the chunks that are compatible with the filter on the query. Chunks can be not just on a single computer, but on multiple of them, on multiple database services, with the abstraction that is called distributed hypertable, where we distribute chunks to multiple Postgres databases that work together and provide a way to scale your time series data to many different nodes. We call this feature a multi-node, and there is an access node that receives user queries and data nodes that contain chunks that the queries are routed to. We support both querying the data and modifying the data in a reliable and performant way. Besides, we provide transparent compression for all the data. The data can still be queried, but it takes much less time, much less amount of disk space. We have continuous and real-time aggregates to convert the raw data into some aggregated results. And you can define data retention policies to get rid of raw data after some time. We provide advanced analytical functions, and we work hard on making queries against huge volumes of time series data reliable and performant. In this talk, I'm going to start by describing how and why we run Postgres and Timescale on Kubernetes. And I will introduce the concept of database forks, clones of the data. And I will describe how do we do database forks and what are they useful for. And in the last part of this talk, I will describe how we use the infrastructure behind database forks to create continuous tests for database backups. So Postgres and Kubernetes, and let me start by introducing some Kubernetes objects that are building blocks to running Postgres on top of them. You can look at Kubernetes as a sort of distributed operating system. In a normal operating system, you have processes, and this is the same in a distributed one. The processes are running inside containers. Basically, a container is powered by a Linux C group, and it runs a immutable image with the applications. Those are typically one or several, and for instance, it could be Postgres. Containers has their own file systems, but this file system is a layered copy of right one, and it is not designed to store database data. Instead, there is a concept of persistent volumes and volume mounts, and volume mounts allow you to mount an external storage into the container. It could be a local SSD disks, it could be an external storage, for instance, Elastic Block Storage in Amazon. And there are many providers that support persistent volumes in Kubernetes. Typically, you store your Postgres data, PG data on a persistent volume. Now there could be several containers working together. For instance, one container to run your database and another container to back up your database. Those containers typically need to share some data or some resources of the host, and they are normally grouped into what is called a pod. A pod is basically a group of containers that share one or several Linux namespaces and therefore run on a single host. Now, in Kubernetes, there are some metadata that is attached to Kubernetes objects. That metadata is typically presented in terms of key value pairs that are called labels. So each label can be attached to a pod or another Kubernetes object, and normally and the labels are normally used to filter on specific types of pods. For instance, you may run your Postgres cluster with several pods. One of those would be a primary, and others would be replicas. And you can define several labels, one with the name of the cluster that all pods will share, and another with the role of the given pod, where the primary pod will have role equals primary, a key value, and replica pods will have role equals replica. So if you need to direct your connections to the primary, we will look for the pod with the label role equals primary. You don't need, though, to filter pods manually to connect to the primary Postgres instance. There is a concept of a service that acts essentially like a socket in your operating system, but it allows you to filter pods that are behind those service based on the labels. So a service can have a label selector that allows to select only a certain subset of pods. For instance, you can have a service for a given Postgres cluster that has a label selector saying role equals to primary, and another service that has a label selector that says role equals to replica. And upon connecting to that service, the clients will be directed to the appropriate pod. Each service has a sub-object called an endpoint, and the endpoint is what stores the addresses of the pods that match the label selector. It is possible to update the endpoint directly, not relying on the labels of the underlying service, and we will see how it is useful for our case. Now we have pods and we have persistent volumes, and we need to bind one to another to run a database. Typically, a database cluster is a set of several pods, one for primary, others for replicas, together with persistent volumes. And we need a property that if a pod is restarted, the same persistent volume is reattached to the restarted pod. And that properties are guaranteed with the Kubernetes primitive that is called a stateful set. It is basically a set of pods with the persistent volumes that contain the state, in our case, PG data. A stateful set also guarantees that an IP address that is attached to the pod will be retained when the pod is restarted. It is very convenient even to run databases. Now, how do we actually define Postgres database? For that, we need what is called a custom resource. It is basically just a YAML definition that is domain specific and has some schema to describe what is there, which is primarily used for validation. In a Postgres custom resource, we can define a Postgres version, resources for the target cluster pods. We can define users, extensions, and many other things that are specific to Postgres. Now, Kubernetes knows nothing about the meaning of the custom resource object. It just provides a storage to store this resource and a schema. And the user is responsible for writing a program. This program is called an operator. And an operator is what reconciles a custom resource, this YAML file, to some Kubernetes building blocks that are required to run what this custom resource describes. And that is called an operator pattern. This combination of an operator and a custom resource is quite common, and people has designed and developed multiple operators to deploy Postgres databases in Kubernetes. This is how the Kubernetes cloud, how timescale cloud looks like. Here is a fork of an existing service. You can see the configuration of this fork, the usage information, the connection string, and this is the end result. But it all starts in Kubernetes with the custom resource object. We have a special custom resource object for timescale DB, and you can see that it also defines resources like the storage volume or CPU. It provides a flag to see if we need to create a backup of this service. And this is not YAML. This is a brief description of the custom resource. If I were to show you YAML, it would take multiple screens. This just shows in brief the name of this object of the custom resource and some parameters that the creator designated as like important ones. So what do we do with this custom resource? Now, this is how we deploy Postgres databases in Kubernetes. And here we have three different parts: the operator, the deployer, and what is running inside the pod. The operator is a custom timescale DB operator that implements the operator pattern that reconciles a timescale DB custom resource, the YAML file, with Kubernetes objects, creating at the end a running Postgres cluster on Kubernetes. We have designed and developed our own operator. We did not rely on existing ones because we also wanted to support a multi-node feature where you can run multiple Postgres nodes kind of together to support huge volumes of data. And that capability was missing in existing operators. So we wrote our own. Briefly, why would you actually run Postgres in Kubernetes? What are the advantages out there? There are quite a few of them. For instance, for our cloud, we provide different combinations of CPU and memory, and those combinations does not map one-to-one to EC2 Amazon instances that we run on top of. And that provides flexibility to the user. And in Kubernetes, one can define pod limits and requests to support this slicing of underlying virtual machines, underlying hosts into multiple pods. Kubernetes makes it easy to automate deploying applications because of the operator pattern and because it provides a way to watch existing Kubernetes objects. So an operator can watch what changes in the namespace and pick up a new custom resource and start reconciling them. And once it reconciles them, it can look for changes in the objects it created. For instance, if a stateful set is deleted by mistake, the operator will create another one. So Kubernetes provides convenient functions to deploy and to support a running cluster, to deploy and support running applications, for instance, Postgres clusters. Kubernetes has a number of readily made solutions for observability, for tracing. There are really a lot of different readily made components that can help you with that. And finally, Kubernetes does not depend on a single cloud vendor. You could run them. You could run your Kubernetes cluster on AWS or on Google Cloud or on Azure or on bare metal. And if your application is written in a way that minimizes dependencies on this cloud vendor and just uses Kubernetes API, in theory, you wouldn't need to rewrite your application. In practice, not many people are migrating between clouds, but it's also very useful for developing applications because you can develop and test them on your local laptop with a local Kubernetes cluster like Kind, and then use that application and run it on your real cluster that is running, for instance, on AWS. Of course, there are not only advantages, but challenges in running Postgres and Kubernetes. The main challenge, one of the main challenges is that Kubernetes defies some assumptions that Postgres makes. For instance, in Postgres, there is an out-of-memory killer that in Postgres, there is an assumption that if Postgres runs out of memory, it gets null as a result of a malloc. And for that, you have to configure your Linux system, say disable after commit for it. But this is, disable overcommit for it, overcommit memory. But that is possible and documented. While Kubernetes is also Linux, it's much harder to configure Kubernetes nodes in such a way that they provide a behavior that Postgres expects. Instead, a typical cluster runs an out-of-memory killer if Postgres runs out of memory, and that is not something that Postgres is designed to handle efficiently. Also, containers in Kubernetes are designed to be immutable, which means that if you want to replace your software inside the container, like upgrading to a new minor version or creating a new extension or installing a new extension, you have to replace the whole container. And that typically bounces the pod. And this is an equivalent of restarting your server. Instead of restarting your Postgres, you have to restart the whole server, and that takes additional time and introduces some new failure patterns. Also, because Kubernetes provides an extra layer of abstraction, it's harder to debug applications because you can have vendor bugs, or you can come across bugs in Kubernetes microservices, or there could be bugs in Linux, and all of that together requires experience and requires more time to find out the root cause. So that said, what is actually running inside the pod? So how do we run Postgres? We know how we deployed the Kubernetes objects, but what is inside? Inside, we have a stateful set. As I said, a stateful set is a Kubernetes abstraction that runs many pods and attaches volumes to it and provides persistent IP addresses. So in that case, each pod runs several containers. The primary container runs Postgres, is managed by Patroni. Patroni is a high availability solution that can work with Kubernetes API to store information about the leader and use that information to switch over if the leader is not available anymore. We use Patroni exactly for that, but not just for that. And I will I will describe our additional use cases for Patroni. In a sidecar, basically in another container, we run pgbuck-rest, Postgres backup and restore solution. pgbuck-rest is both creating backups of running Postgres instance and is responsible for shipping rows from the main container. The backups and rows are stored offsite. We use S3 for storage, and Patroni updates endpoints directly. I told that endpoints can be updated by label selectors on the services, but they can also be updated directly, and this is what Patroni does. When Patroni updates the endpoint, it writes the address of the primary together with some service information, and that is used to direct clients to a primary or replica pods. And that also ensures there is only one primary. Also, endpoint updates are atomic. And we use cron jobs, which are equivalent to the operating system cron jobs, to produce regular backups. And we also have config maps which are equivalent to configuration files in your operating system. And in those config maps, we provide configuration and scripts for patroning. Some people use Docker image to provide that. However, if you use a Docker image and you want to change that, you have to replace Docker image, and that requires building new one and bouncing the pod. That is expensive, and that requires a downtime. And in our case, we can just replace either patroning configuration or scripts right away on the fly. And when we edit those config maps, they are automatically, they're reflected in changes in files inside the pod. So this is very convenient, for instance, if you want to test our scripts. So database initialization is something that patroning helps us with. Typically, to initialize new Postgres database, you have to run initdb. Patroning runs that, but it also allows a custom bootstrap script to bootstrap your database in a way that you like, and use it to restore an instance of the database. By the way, we call it the service in timescale terminology. We use it to restore a service from S3 using backups and rows if they exist, or we use it to initialize a fork. Basically, take existing data from one service and use it to create another service. And as I said, this bootstrap script is located in a config map, so we can always change this config map when we kind of roll out the new version of the operator and make improvements very fast. Database forks that I mentioned, what are they and why are they useful for? Basically, a call fork an independent copy of your database at a given point in time. And forking is useful for many different purposes. Basically, you have a copy of a production time and a point in time, production data at a point in time, and it can be used, for instance, for performance tuning if you want to change some parameters of the server that, for instance, requires restart or play with them. This is very useful to run on a fork, having the same data as your production server. You can use it for query optimizations. Also, if you have queries that are, for instance, changing data, or you have multiple queries that you don't want to run in your primary system because it can affect the performance of your production application, you can fork your database and run and use these fork for query optimizations. You can use fork to test potentially dangerous data changes. If you want to run an update on most of your data, you probably want to try it out first on some copy of your data before running it on your production database. And this is where fork is also useful. You can use it to test Postgres major upgrades or other maintenance operations, because major upgrades may fail if you have a non-standard set of extensions or if you have some data that conflicts with what PG upgrade does. And you can fork your database and run PG upgrade on the fork to be sure that it will succeed on the production database at the point where you put your application on a pause to do the upgrade. You can use forks to migrate to a different system, to a different combination of resources without stopping your production database. And you can also use fork to copy your data and then delete some of it, for instance, leaving your old data on a separate instance, on a separate service from your production data. So forking is quite useful. And the question is, how do we fork? And there are many ways to do this. One, and the most known one, is to use a copy and write file system like ZFS. If you use ZFS, you don't really copy your data, but they basically copy pointers to the existing blocks unless you start modifying them. That is quite performant and very convenient, but it typically works if you want to copy your data inside a single system. For us, because we don't want to touch the original system and create a fork on a completely different pod, ZFS is not a solution. However, there are others. There are snapshots provided by vendors like AWS and Google basically take a persistent volume like EBS and snapshot it block by block, and then allows to use that snapshot for copying that data elsewhere. You can, of course, use Postgres point-in-time recovery feature. Basically, you create a base backup and then you ship those to some storage, and then you use a combination of that to recover your Postgres cluster to a given point in time. And the important part is that whatever you choose, you want to combine this with Postgres facilities to create base backups. Basically, you want to archive those, and you want to restore those flows once your fork is running. And you probably want to start stop backup before starting to create a fork and once this is done. So Patroni Custom Bootstrap that I mentioned before basically runs a user-supplied script instead of an ETB, and it has certain restrictions. Patroni Custom Bootstrap requires a cluster to be a brand new one. We store initialize key in the consistency layer, and if this initialize key is already present, Patroni will recognize that it doesn't need to bootstrap the cluster, but it has to, say, create a new replica in that cluster and will not run a custom bootstrap script. Also, if there is an existing data directory, Patroni will treat the instance as crashed and not new, and will not run a custom bootstrap script. Patroni has a YAML configuration, and in this YAML configuration, you can have a method. There can be different ones, and for each method, you can provide a command that runs this custom bootstrap. So our custom bootstrap relies on an open source Postgres backup and restore solution that is called pgback REST. It's very flexible. It can be configured with environment variables, which is what you typically, how you typically configure your pod. A pod is has a container, and through this container we pass some data in the form of environment variables. It supports multiple cloud providers like S3 out of the box and can ship those and backups to S3. It's very flexible, and it has different targets for point-in-time recovery. For instance, you can do a point-in-time recovery to a given named target, to a given timestamp, to a given transaction. Basically, everything that is supported by Postgres is supported by pgback REST. And below we have a command that runs pgback REST. We provide a path to the Postgres data directory. We have some S3 parameters to point to the S3 folder and bucket where the backups are stored. And we also have a target, which is a recovery target that instructs the recovery to stop at a certain point when restoring data. So this is the bucket and the folder inside S3 point to the parent service, to the service that we are trying to fork. And it works by basically a fork starts, runs Patroni bootstrap scripts, restores a base backup, and then it restores those segments from S3 up to a given recovery target. So we use a named recovery target with a command that is called pgcreate restore point, passing it a certain name, and then we also do a row switch right afterwards. So we do this to avoid an infinite recovery time. If your parent service is actively writing row segments and you don't specify a recovery target, a recovery may continue restoring those row segments. And if recovery is slower than the ratio of writing rows at the parent side, then it may not stop in a reasonable amount of time. By providing recovery target, we do this we ensure a predictable time to start the fork. And we also switch rows to make sure that all segments up to the one that contains the recovery target are available to be restored. So the recovery point and recovery target is propagated from the deployer to the target pod. Sorry, from the deployer to the target pod basically using the custom resource definition. When deployer initializes the fork, it connects to the source instance, and then it runs those commands to create a restore point and switch rows, and then it memorizes the name of the restore point and writes it into the custom resource. When the operator reconciles a custom resource, it creates a stateful set with the pods, and for the pods, it defines environment variables with the name of the target of the parent service and with the recovery target name. So once Patroni inside the fork takes over and basically runs custom bootstrap, the fork takes the name of the parent instance, locates the bucket on S3 where the parent data resides, and then restores that parent data up to the recovery target. So Bootstrap process for forks initially just restores the base backup using pgbackRest. Then pgbackRest writes a recovery section in the postgres.conf that used to be recovery conf in older versions of Postgres. And we start Postgres and wait until it recovers those segments up to the recovery target. And once Postgres recovers that, we have the recovery action promote. So Postgres must promote at the end. We'll wait until Postgres promotes and then stop Postgres. And once it is stopped, the script returns 0. And that puts Patroni in charge. So the bootstrap script returns to Patroni. Patroni recognizes then the backup is finished and starts Postgres instance as a primary and takes over. One issue that we came across when debugging this procedure is this error message about not impossible to run hot standby because of mismatch of some parameters between the parent and the fork. Because we allow forks to have their own configuration, and we actually auto-tune forks based on their resources. It can be that fork has different values for max worker processes or max connections, and that would stop fork from recovering because of this mismatch and inability to run hot standby. Excuse me. Because we don't really need hot standby when we initialize the fork. We actually disable it when writing the recovery section, when I didn't something to the recovery section, pgbackRest writes. We also disable archive command because we don't want fork to archive to the bucket of the parent instance. And this can be also done by Patroni because Patroni also knows to disable hot standby in the custom bootstrap. This would require us to create a recovery conf section for our custom bootstrap method. There are some minor issues with that, so we decided to go with our own way of doing custom bootstraps, where we first rely on pgbackRest to write a configuration, and then allowed Patroni takeover once Postgres reaches consistent state and promotes. One issue that we found is what if the bootstrap process is interrupted? Basically, if the bootstrap process fails and the script returns non-zero, then Patroni knows how to handle it. It understands that the bootstrap has failed and retries it. However, in Kubernetes, what could happen is that the whole pod disappears, and once it returns back, Patroni starts. And as I described before, when Patroni finds a Postgres data directory that looks legitimate, that exists, that has files in it, then it doesn't run a custom bootstrap script. Instead, it treats this as a Postgres crash and just tries to start it and then takes over. Because in that case, custom bootstrap will be unfinished. We will not run post and init scripts that create rows and set up the cluster, and it may even not recover all those segments. That leads to a failed fork. And it is possible to get around this. For instance, when the Bootstrap is running, we can annotate the pod saying that Bootstrap is in progress. Pods annotations are another piece of metadata. Basically, similar to labels, it's key value pairs, but it's mostly used not for filtering pods, but by telling some additional information for the running pod. So we can create an annotation from inside the pod. Because Kubernetes talks a REST API, it is possible to basically use whatever, even bash scripts, to talk to Kubernetes and annotate the pod. So we could annotate the pod saying that the custom Bootstrap is in progress. And then when the pod restarts, the init script in the Docker image can look for that annotation. And upon finding that the custom Bootstrap was still in progress, it will move Postgres data directory elsewhere and allow Patroni to see an empty data directory, an empty mount for the data directory, and allow Patroni to start the Bootstrap instead of the recovery procedure. One idea is to build it into Patroni, because nothing prevents Patroni from tracking the Bootstrap in progress inside DCS, inside this consistency layer. It is called distributed consistency system. And upon finding out that the key in DCS exists, it may recognize an interrupted Bootstrap and act the same way as if the Bootstrap script returned non-zero. Monitoring for Bootstrap is another problem that we came across, because the Bootstrap time depends on the size of the fork and also on the configuration of resources of the target instance. We cannot predict how much time it would take to Bootstrap. So we cannot create an alert that would act if Bootstrap takes more than expected. We basically don't know the expectations. So when backup is restored, but on one of those steps, on step 2, when Postgres replace flows, it fails. At this point, the pod is just stalled, Postgres terminates, Patroni cannot do anything with that because it waits until the custom Bootstrap script finishes. The custom Bootstrap script just waits until Postgres reaches consistency state and becomes available for writes. So nothing is moving, basically. And this can also be solved by communicating a failure using pod annotations. So basically, at a step where Postgres is started and the backup and the raw files are restored, we can look for running Postgres processes. And upon finding none of those, we can immediately annotate the pod with notation saying that the Bootstrap has failed. And the deployer service, the one that monitors a running instance and looks at its current state, can also watch for the pod, basically subscribe to its changes. And upon finding an annotation on the pod, it will recognize that the fork has failed, and it will, for instance, delete the pod and the persistent volume and initiate the process anew. Or it can sort of put the pod into the take the volume and preserve it so that it can be analyzed in case fork fails repeatedly. So what are the next steps? We have forks already. Those are basically point-in-time ones. But we can improve it, and we can come with some other ideas based on forking. One is provide a point-in-time recovery in the past using forks. So right now we clone to the present state, but we can easily clone to the previous state as long as we have backups and woes. We just provide a certain time-based target. And if the user wants to recover a table that has been deleted 1 hour ago, it can just fork to a state 1 hour ago and take this table and dump it and then restore to the primary instance. We can have follower forks that I will describe in a minute. And then we can also have custom volume snapshots. We can have volume snapshots, which can speed up creating of forks compared to S3 backups. So what is a follower fork? A follower fork is basically a fork, but it is not detached immediately from the original cluster. So it replaces all files as if it was a replica, as if it were a replica, until it is manually promoted by the user. So in the picture, you see a primary cluster, it runs a primary service and then replicas. And there is also a follower cluster that doesn't have a primary, but has what we call a leader replica. A leader replica fetches changes from the primary. The primary may not be even aware of the presence of this leader replica, and can also have some cascading replicas of its own. So Patroni supports this with the help of the feature that is called a standby cluster that allows you to configure exactly this configuration. And then a standby cluster can be detached automatically, can be detached manually from the primary one and become its own cluster. And we can use this feature to provide follower forks. And for follower forks would allow you to, and the follower forks would allow you to pick an optimal point in time where you want to detach your follower cluster from the original one. So it can provide migrations, for instance, with minimal downtime. We can use snapshots instead of S3. So Kubernetes volume snapshots are basically abstraction of vendor-based snapshots, like, for instance, AWS snapshots or Google snapshots. And a snapshot is a copy of a block device, block by block. They are typically incremental. If you have already created a snapshot and create it again, it will only copy blocks that are different. They are typically more or less atomic. And Kubernetes supports creating new volumes, not from scratch, but from an existing snapshot. So if we created a snapshot of our primary service, we can use it to create a fork volume that is faster than creating them using pgback rest backup restore, or a backup restore with other solution if the data is located on S3. Apart from faster recovery time, snapshot allows you to do incremental changes no matter which Postgres version is running on the target volume. pgback rest also supports full and incremental backups, but in order to run incremental backup, the original full backup and the incremental backup you're trying to do have to have a matching Postgres versions. If you did an upgrade from your from the time when you created the full backup, the next backup cannot be incremental; it will always be full. And snapshots allow us to only snapshot incremental changes, to only snapshot changes since the previous snapshot. This is very useful for things like upgrades, because in the case of upgrades, we can create a snapshot of the original service, upgrade it, and then only pick up the small amount of changes after the upgrade and provide a backup in the form of snapshot just before we put the upgraded service online. It's not possible with the backups on S3. However, snapshots, if used with forks, require some hacks. First, there is no support for pgback rest. It is possible to still use pgback rest, but we will require a flag that is called delta, where pgback rest will not replace your data directory, but it will analyze the contents of your data directory and what is available in the backup storage, and only ship changes to your data directory. So the idea is that we can create a volume from the snapshot and then run pgback rest in a delta mode to get the changes. Patroni, as said, does not activate the bootstrap mode if there is a valid pg data directory. So to work around, we have to rename pg data in the snapshot or in the init container that runs before we run the main Patroni container. And then in the custom bootstrap script, we have to recognize this rename directory and rename it back. So one idea for pgback rest is to have extendable hooks that would allow you to provide a user-supplied callback for creating backups, not with the built-in method, but with something else, say AWS snapshots. So given that, I will briefly describe how we use this infrastructure, not just for forks, but also for creating continuous tests for database backups. You'll probably know that a backup is not something that people not something that people are interested in. People typically are interested in restoring a backup. And normally you cannot just test a backup of your service, but restore it in place, because that will destroy your original service and put a downtime. But we can use forks, because forks are creating as the same service. And the fork is basically the procedure of restoring a backup from S3. This is very convenient. We can create a fork, and we can also instruct the fork not to detach and run its independent service, but instead run pgdump schema only to test that the schema is consistent, and at least we can dump it. We cannot test all hundreds of instances at the same time. That would be quite expensive and unnecessary load on the network and disks. But we can pick n services at a time and look at an individual service to see if that service has already been tested some time ago. And depending on that, either run the test or skip to the next service. So we use the fact that Patronia updates the endpoints every event loop to update the leader information. And we watch in Kubernetes for the endpoint. And upon watching for the endpoint, we look at this cluster and see if the backup has been created recently, if the backup test has been made recently, and if we already have a certain amount of backup tests running. And if this service is eligible for a backup test, and we still have spare workers, we basically create this what we call restore test, special type of fork that is not available to the user. We don't create a service for it. The user cannot connect to it, but it also runs some additional tests on top of just restoring a fork. As I described it, for instance, runs pgdump. And the deploy service connects to the restore tests. Here is basically the picture of what we do to create these restore tests. First, the deployer listens for the service endpoints, watch for the updates, decides if the service needs a restore test. Then the deployer creates the restore test, initializes it, basically creating a fork. A fork restores information from the original service from S3, runs, and then runs some pgdump commands. And then the deployer connects to that fork once it is online and reads the information from the tests, and then puts this information in the cloud management database. And then we can have a Grafana dashboard and alerts on the failed restore tests. So this way we can test backups of all our fleet without overloading the infrastructure and without destroying the original services, just using the forking. Yeah, so that is it. Thank you very much for listening to this talk. You can ask me questions using my email, or you can ask me questions on Twitter. Thank you very much.